Hello, this is Richard Hammock's Calculus 1. We are in Part 5 of the course on integration. This is Lecture 44b, More Substitution Examples. In Lecture 44a, we learned about the substitution rule. If u equals g of x, then the integral of f of g of x, g prime of x dx equals the integral of f of u du. It says that if you make the right substitution, u equals g of x, you might be able to convert a complicated integral into a simple integral that's easy to find. And we looked at a lot of examples of using the substitution rule. And today, we'll just continue with more examples. Let's start out with some easy examples. These are integrals that you can actually do in your head, although we'll alternatively use substitution for them. Think about the integral of cosine of 2x dx. You probably have enough experience with integration to immediately recognize that the answer is 1/2 sine of 2x plus c. The reason is that if you differentiate 1/2 sine of 2x plus c, you're going to get 1/2 cosine 2x times 2 by the chain rule, and the 2's cancel, and leaves you with just cosine 2x. But imagine you didn't see that this integral equals this. I'll gray out that solution, and let's use substitution. The integral that we're dealing with most closely matches the integration formula, integral of cosine u du, which is equal to sine of u plus c. So here, what we'd want to do is make the substitution u equals 2x to convert this integral into the simple one. So u is equal to 2x, but then we have to do a little computation to make sure the dx matches up with the du. So we take du dx, which is 2, cross multiply, du is 2 times dx, and you can see right there, du is not equal to dx, it's 2 times dx. So this dx right here, it's not equal to du. But let's multiply both sides of this by 1/2. We get 1/2 du equals dx, and that tells us this dx can be replaced by 1/2 du. So making those substitutions, the 2x changes to a u, the dx to a 1/2 du. The 1/2 is a constant that can factor out of the integral. We get 1/2 integral of cosine u du, and we have an integration formula for this integral. It's sine of u plus c. So multiplying through with the 1/2, you get 1/2 sine of u plus c. All we have to do now is change that u in our answer to a 2x, which it's equal to, and we get 1/2 sine of 2x plus c. There's our answer. And it matches up exactly with what we got in our heads here. Let's try another one. The integral of e to the minus x dx. Well, you've probably done enough integration to immediately recognize that this integral equals minus e to the minus x plus c, because if you differentiate minus e to the minus x plus c by the chain rule, you get e to the minus x. But imagine you didn't see that. Let's use substitution to find this integral. So I'll gray out the answer there. With substitution, you look at this integral and say, it looks a lot like the integral of e to the u du, which we have an integration formula for. But the u would be equal to negative x. So u equals minus x, du dx equals minus 1. Multiplying both sides by minus dx, we get minus du equals dx. So this dx that's right here, it's equal to minus du. So we make these substitutions. The minus x is a u, the dx, as we computed here, is a minus 1 du. And the minus 1 can factor out. We get negative integral e to the u du. And by an integration rule, that integral is e to the u. So negative e to the u plus c. And now plug in the minus x that u is equal to, and there's our answer, minus e to the minus x plus c, the same answer that we got up here in our heads. But it's comforting to know that substitution gives you exactly the same answer. For our next example, think of the integral of cosine x squared 2x dx. This is also one that you can probably do in your head. Even before you learn substitution, you'd probably recognize that this integral equals sine of x squared plus c, because if you differentiate sine of x squared plus c, you get cosine of x squared times 2x with the chain rule. So we got that in one step. You can also use substitution for this. You'd let u equals x squared, so du dx is 2x. So du is 2x dx, and make those substitutions, and you get exactly the same answer. But the point I want to make here is that you can often skip steps just with your knowledge of integration. Sometimes where substitution applies, you can just look at the integral holistically and see what the answer is. And that happened for all of the examples on this page. Other examples are less obvious. Think about the integral of secant squared square root of x over square root of x dx. When you look at this, you see the secant squared, and we know the integral of secant squared u du is tangent of u plus c. So that suggests we want to hone in on this secant squared square root of x. Let's split that off and write this as the integral of secant squared square root of x times 1 over square root of x dx. And notice that that looks like the integral of secant squared u du. So let's see if we can use substitution to convert this integral into this familiar one whose answer is tangent of u plus c. Well, clearly what you'd want to do here is let u be equal to the square root of x, because that's what's inside secant squared. So u is the square root of x, which is x to the 1/2. Let's compute du dx. You get 1/2 u to the minus 1/2, or 1 over 2 square root of x. Multiply both sides by dx. We get du equals 1 over 2 square root of x dx. Now, here at the end of our integral, we have 1 over the square root of x dx that almost exactly matches what we have here, except there's a 2 at the bottom. So no problem, multiply both sides of this equation by 2. We get 2 du equals 1 over the square root of x dx. So that tells us that this 1 over square root of x dx right here equals 2 times du. So we can make those substitutions. The square root of x is a u. The 1 over square root of x dx is a 2 du. And then we can factor out the 2. And now evaluate this simple integral of secant squared u du is tangent of u plus c. So bringing down the 2, we have 2 times that. Next, plug in the u equals square root of x in our answer, and we get 2 square root of x plus c. That's our final answer. And you can check this, you can differentiate this answer, and you will get the integrand. Another example, the integral of cotangent x dx. It's a pretty simple integral, but we do not have any integration formula for cotangent x. So what could we do? Why don't we try writing that cotangent of x as a cosine x over sine x? So we've converted to this integral, just with a trig identity. And let's think about that. Up at the top, you've got a cosine of x. At the bottom, you have a sine of x. Let's split that up and write it as the integral of 1 over sine of x times cosine x dx. What could we do there? Well, look at the 1 over sine of x. Imagine that u is equal to sine of x. This would be 1 over u. And then du dx would be cosine of x. So that looks promising. This integral looks kind of like the integral of 1 over u du, where u is equal to sine of x. So we'll make the substitution, u equals sine of x. If we do that, we have to look at du dx. It's cosine of x. So du equals cosine x dx. Perfect. The cosine x dx that's right here, it equals du. And that sine of x is u. So this integral converts to the integral of 1 over u du. And that's ln of the absolute value of u plus c. Plug in your u equals sine of x. And there's the answer. ln of the absolute value of sine of x plus c. We've just found this integral with substitution. Here's another example. The integral of 3 over the square root of 5x minus 1. Let's factor out that 3 at the top because it doesn't really seem to be doing anything for us. We get 3 times the integral of 1 over the square root of 5x plus 1 dx. And that looks something like the integral of 1 over the square root of u du, which you could integrate because that 1 over square root of u is u to the power of 1/2. You could use the, or negative 1/2. You could use the power rule for integration there. So if we want to convert this integral to something that looks like this, that u would have to be 5x minus 1. So let's try the substitution, u equals 5x plus 1, minus 1. Well then du dx would be 5. Du would be 5 times dx. So you can see here this dx right there, it's not equal to du. But we could get a match by multiplying both sides of this equation by 1/5. So 1/5 du equals dx. So there we go. This dx equals 1/5 du. Now let's make those substitutions. We bring down the 3. We get 1 over the square root of u. And this dx converts to a 1/5 du. Now the 1/5 we can factor out of the integral. So we get 3/5 integral of, this is u to the power of negative 1/2 du. So there is an integral we can use the power rule for. So we get this. Simplify those fractions. And simplify further. The answer is 6/5 square root of u plus c. Now, of course, we're not completely done because we now have to plug in the u equals 5x plus minus 1 here. But doing so gives us our answer, 6/5 square root of 5x minus 1 plus c. New example. Integral of x cube root of x plus 9 dx. Your experience with this tells you that you probably would like to convert this radical to a power, x plus 9 to the power of 1/3, and there's an x out in front. You know by now that that's likely to be part of your du, so let's bring that x over next to the dx and convert this to the integral of x plus 9 to the power of 1/3 x dx. So we look at that and we ask ourselves, can we make a substitution that turns this integral into the integral of u to the power of 1/3 dx? Well, yes, it looks like u equals x plus 9 might get us there. So let's try it. U is equal to x plus 9. So du dx is 1. That's nice. And look at that. Du equals dx. So in this integral, we can replace the x plus 9 with a u and the dx with a du. And that looks great, except there's one little problem there. What about that x? It wasn't a part of the du. Making these two substitutions gives you the integral of u to the power of 1/3 x du. And you got a mix of of x's and u's there. And that's not good. You need to convert all the x's to u's. So unfortunately, it looks like we don't have a match for du here. Du is equal to dx, and we have x dx. So what are we going to do? Do we start over? Well, in this case, we don't have to, and I'll show you why. Look at our expression for u. It's x plus 9. And then here we have an x. Notice we can solve this equation for x. I'll do it down here. We get x equals u minus 9. Just subtract a 9 from both sides of this equation. And so now that this x that's here, we can see that's equal to u minus 9. So now we have 3 substitutions that we can make. This integral now becomes the integral of u to the power of 1/3 times the x, which equals u minus 9, times the dx, which equals du. So that's good. It's all u's now, and we can move ahead with this. We can multiply the u to the 1/3 into the parentheses, distributed in there. You get the integral of u to the 1/3 times u minus 9 u to the 1/3 du. And let's combine these two terms. That's u to the power, integral of u to the power of 4/3 minus 9 u to the power of 1/3 du. And for these two terms, we can integrate them with the power rule for integration. So doing that, we get this expression minus this one, plus a c. We'll simplify those fractions and simplify further. We get 3/7 cube root of u to the 7th minus 27 over 4 cube root of u to the 4th plus c. And you may want to pause the video to double check my arithmetic here. But once you do that, you're almost at your answer. You've got 2 occurrences of u here and here. We've got to change that to an x plus 9. So doing so gives us our final answer. So every once in a while, you'll find an integration problem like this where you'll make a substitution and you'll discover that you are left with the x term in there that's not accounted for in your substitutions. And every once in a while, you can do a trick like this where you solve for that x in terms of u, and everything is good. So that's pretty much it for today. We've had more practice with the substitution rule. I want to emphasize that as you work with the substitution rule, you're going to see shortcuts and steps you can bypass, and that's good. I'll do one final example to illustrate that. Integral of 5x cosine x squared dx. After you've done a bunch of substitution problems, you'll realize that that 5 is doing nothing for you, and you're going to factor it out at the beginning. And the x, you expect that to be part of your du, so we're going to bring that over to the dx, and we get 5 times the integral of cosine x squared x dx. Now at this point, you may not even write the substitution off to the side. You'll look at that and say, okay, u is going to be x squared, so du is going to be 2x dx. And that doesn't quite match the x dx that you have right here. So in line, you will just replace that x with a 2 times x. But you have to also divide by a 2 on the outside to cancel with the 2 that you just inserted to make sure that these two integrals are equal. But in doing this, now this 2x dx, that equals your du for when u is equal to x squared. And then you can do the substitution in your head. You get 5/2 sine of x squared plus c. And you can check that by differentiating this answer. You do get 5x cosine of x squared, so it does work. So I invite you to take these shortcuts. In doing the exercises, it's a good idea not to skip too many steps because you can easily make mistakes. So be careful. But as you work these problems, it's going to start to come together, and you're going to get your answers more and more quickly. That's it for today. Coming up next, we're going to look at more substitution, but we're going to look at substitution in definite integrals, not indefinite integrals, like we've been doing today. So I'll see you then, and goodbye.